Welcome to the first part of our third PSpice demo. So I'm going to go ahead and start a new project here, and we'll call this demo number 3. And I'm going to leave all of that fixed, and let me put this with our other demos. And what we're going to be looking at today is we're going to be looking at making a filter circuit. Let's put that in there. Okay, and we're going to create a blank project. So what we're going to do with this demo is we have actually looked at a filter circuit in the notes. So while that's loading, let's take a look here. So we had considered this circuit from the notes when we were looking at filters. And through our analysis, we determined this was a low pass filter. And we were able to determine also our corner frequency, or our 3 dB frequency of 118 Hertz. So what we're going to do now is we're going to verify that using PSpice. So we have a 2 Henry inductor, and then a 2 k ohm resistor and a 2 microfarad capacitor in parallel. And of course, we have this AC voltage. So let's see if we can't verify those results. So I'm going to come over here to my parts. So in my source library, I can find VAC, which is going to be an AC voltage source. And we're going to look at something a little different in a later video. But right now, we're just going to use this. And as we're going to see, we're going to be able to sweep our frequency for our simulation. So we're also going to need an inductor, which is part L in the analog library. So let's put that right here. Let me go ahead and again hit an escape to stop placing parts. I'm going to zoom in so we can see a little better what I'm doing. So now I'm going to look for a resistor, also in the analog library. I'm going to click R once to rotate that. Escape to stop placing, and I'm going to come over here and look for a capacitor, which is part C in the analog library. Again, I'm going to click R to rotate, and I'm going to place that in parallel with my resistor. The other thing we're going to need is a ground, so I'm going to hit G to place a ground. Again, any of these should be fine. I'm going to click OK. I'm going to place my ground down here at the bottom. Okay, so now we're ready to start wiring, so I'm going to go ahead and wire everything up just like we had in our circuit. Something like this. And after I finish wiring, I'm also going to go ahead and place a couple of net aliases just to make it a little bit easier to identify our input and output. So over here on the toolbar, place net alias. Let me label my input over here on the left. So that's going to be my input voltage. And let me also label my output. And that's just going to make it easier. And so again, just going back to our notes for a second, we notice that our output is defined, well, I suppose it's not written explicitly here, but our output should have been defined as across this resistor and this capacitor, the voltage here. So we can see that from our equation here. Okay, so going back then to our simulation, let's adjust these values. So we had a 2 Henry inductor, we had a 2 k ohm resistor, so we'll change this to 2K. And we had a 2 microfarad capacitor, so 2U for 2 micro. And for right now, I'm going to leave the magnitude of my AC voltage at 1. The reason that is sort of an attractive thing to do is, remember, our transfer function can be used to get our output from the input. So we can say our output, Y, is equal to the transfer function times the input, so H times X. Well, if our input is just 1, then we can say that our output is equal to the transfer function. So one thing we're going to do is look at some Bode plots of our transfer function. And if our input is just 1, then our output is essentially just going to be our transfer function in this case. Okay, so we've got our circuit wired. We've got all of our parameters set how we want. So now we need to come up here and create a simulation profile. So let's call this simulation profile AC sweep, because we're going to be up, and again, it's getting upset with me because I can't have any spaces here, so I can put a hyphen or underscore. So we're gonna choose a different analysis type from what we've done before. So from analysis type, we're going to select AC sweep / noise, and in doing so, we notice we're by default going to have the ability to sweep through our frequencies. So in this case, we know our corner frequency. Well, we've calculated it should be 118, so we want to be well on either side of that. So let's go ahead and say 1 Hertz for our start frequency, and let's say 10 kHz for our end frequency. And so remember, this is going to be plotted on a log scale. So that's the reason we can have this relatively wide range. And then points per decade, this is just going to affect the resolution. Let's start with 100 points per decade and see how that goes. Okay, so let's click OK there. And so what I'm going to show you is how we can get our Bode plot for our transfer function. Again, in this case, our transfer function is equal to our output because we have a 1 volt input. So I'm going to show you a general way to do that from our output window. But I also want to point out you can do it with markers if you like doing that better with probes. So if you come up here to PSpice and markers and then advanced, you'll notice we have options for dB magnitude of voltage. So that can be used to get the magnitude part of our Bode plot. And then we also have, for instance, phase of voltage. If we're talking about a voltage output, of course, that could be the phase part of our Bode plot. So that is an option that's available to you. Personally, I prefer to just use the more general method, which I'm going to show you here shortly. Okay, so it's working on it. So let me pull this up and over to this screen here. So 100% complete. So now what we're going to want to do is we can add a trace, just like normal. And so notice here's my input and output. Remember, I can filter it down to just voltages. If I have a lot of components, that makes it a little easier to see. But let's say, so we're looking for the Bode plot of our transfer function. So if we want to keep this really general, let's say our input could have been any voltage 1. So what I'm going to do for my decibels is I can use this function here, dB, and then I'm going to say it's the dB of what? Of our output voltage. And again, in this case, that would be fine because our input was 1. But to be more general, I can come in here and I can put that it's output divided by input. And again, I'm just selecting whatever is my input and output here. And you can also type that directly into the equation box here. And so we get something that looks like this. And so we notice this doesn't quite look like what we expect from a low pass filter. We have this sort of little peak here indicating that we actually have some gain. So 0 dB would be 0 gain. It'd be a gain of 1. So we're passing the signal, but we actually have an increased gain here. And so this is due to a resonance effect. But what we're ultimately going to be interested in is finding that 3 dB frequency. And so our 3 dB frequency is, of course, where we've gone down 3 dB from 0. So in order to find that, we can use this cursor function. So I'm going to click to toggle cursor on. And so now if I use my right and left arrow keys, I have this red cursor that's going to follow along the plot. I can also left click on the plot anywhere, and that's going to take the cursor approximately to that point. So maybe I say, looking at this plot, we've got -20, so here's 10, so here's 5, so -3 is going to be about here. So I say, well, it's going to be about this frequency here. And then it's very small and difficult to see, but down here we can look at the values of this cursor. So our red cursor is this value here, so we have X value and value of this dB. So right now we're at 115, and we're at -2.4 for our dB. So we want to get that to 9, so I'm going to use my arrow keys and just go a little bit over until I get to approximately -3. And so it looks like this is as close as we can get. And so on either side, of course, we can see right here, we're essentially at our calculated frequency of 118 hertz. So we have good agreement with what we found previously in our notes, which was a corner frequency of about 118 hertz. And again, that corner frequency is just where we've dropped 3 decibels below this sort of low frequency pass, because again, this is a low pass filter. So let me turn this off for a second. And so if we wanted to have the full Bode plot, we would also need phase information. And oftentimes for Bode plots, we have both magnitude and phase shown at the same time, but of course not on the same plot. And so there's a couple options that we can do. The first thing we're going to do either way is we want to make a new window. And with our new window, we can now plot the phase. So for our phase, over here in our functions, we can select P. which is going to give us the phase. And we're going to do the same thing. We want the phase of the output. In this case, that would be fine because our input was 1, but to be more general, let's come back in here and put output divided by input. And we have our phase here. And so over here on the left, we see -0 degrees. And then as our frequency progresses at high frequencies, we're at -180 degrees. And so if we want to see both the magnitude and the phase response at once, we can come up here to Window, and we can choose either to tile horizontally or vertically. Typically with our Bode plots, we see them tiled horizontally such that we have the same sort of frequency scale. So if we wanted at that corner frequency, we could come up here then, we could turn our cursors on, and we could figure out what our phase is at that corner frequency of 118. So we have to go good ways here. So we see we're getting closer. So around 118 degrees, we have about a -148 degree phase. So that covers it for this first part of our third demo. What we're going to look at next time is we're going to come back and we're going to replace this with a sinusoidal source, and we're going to manually adjust the frequency and see what it looks like when we have a frequency that gets passed by the filter, a frequency that gets blocked by the filter, and a frequency that is at that 3 dB frequency.